So to graph that particular function that we talked about like last class, you could start, you go to this website and you can type in y equals x squared, and you see that you get this red curve here. Then you could type in another function, let's say x minus 2, the exponent 2, and you get the blue curve. And you see it shifted to the right, even though I have a minus in here. The next one would be y equals 1 over 2 times bracket x minus 2, exponent 2, and it flattens out with that half. Then you could put a 2 over in front. And you get the purple graph. Now we want to flip it. And then you get that black curve that flips. And the last one would be a vertical shift. And then it shifts up 3 units. So you can play around with this grapher to help you with your assignment or with just checking your work to make sure you can plot it correctly. So here today's class, we're going to essentially be talking about even odd functions, some different product and quotient of functions, the composite of functions. That's a very important topic. Sorry. Let's just put a little star beside it. If you've never seen this before, it is something that is used frequently, and the decomposition of functions. So what are even functions? So a function is even if, by definition, the function where there's a negative x is equal to f of x for every x in the domain of f. So this is the definition here. So the function f of x is even function, but what is f of x first? What do I mean by this f of x? Well, we're kind of talking typically about these things called, suppose f of x is of this format. A naught plus a1 x1 plus a2 x to the power 2 plus a3 times x to the power 3 plus dot, dot, dot. So this is a polynomial of this format. And this a1 is called the coefficient. So it's something like you've been used to, but this is general. So it's a naught times x to the power 0, anything to the power 0. This is 1, so it's a naught. So this is our polynomial. So this function of this format is an even function if all the powers of x in f are even integers. So they're even integers. So the powers have to be even. So this 2 is even, the 1 is odd, the 3 is odd, etc. But they are, of course, the 0, well, we'll get to that. But there are, of course, many other even functions. So this equation, again, that's like by definition, holds for every x in the domain of f. This expression, negative x of f, must be defined to start with. So for example, a function whose domain is on this interval, -4 to 2, cannot possibly be even function because the domain extends all the way to -4 on the left, but only 2 on the right. And we're going to talk about that in a second. They have like this thing called a symmetric property. So some examples here. So f of x equals x squared, our favorite function. By definition, we're going to check that equation. So f of -x is just going to be equal to -x squared, which is just equal to -x times -x, which is our x squared. Oh, look, like they equal the same. So by definition, f of -x is equal to f of x. So therefore, f of x equals x squared, and this is therefore an even function. And you see, because it's to the power 2. And we use this kind of logic, like we use the definition, we check the left-hand side, the right-hand side, to see if things are even or odd, or just in general in other questions in mathematics. What about this example here? Function like this. Is this even or odd? Yes? Why? Yes, on the back?
It'll be odd because the x to the power of 5.
Right, yeah. So this 5 is an odd number. What about here? There's another reason too. Yeah, so x to the power, it's like an imaginary 1 here. So that is also an odd number, right? It's 1. 1 is odd, right? So therefore, let's go back to our blue. This is not an even function. Because some powers, just writing a statement here, of x are odd numbers. And you can also see by the definition that f of x is not equal to f negative x. So for example, f of x is equal to this, just the function written out again. But we're going to see that f negative x is going to be equal to 6 times negative x to the power 5 plus 4 times negative x to the power 2 plus 2 times negative x. So negative x to the power 5 is sort of like a negative goes out front. You get negative 6x to the power 5. This one is the same because that's even. minus 2x. So you see that they're not the same. So this one and this one, they're not the same. So f of x does not equal f of negative x here. What about down here, another example? So let's say this is example, let's just label them 1, 2, example 3. What about f of x is equal to x to the power 8 plus 7x to the power 4 plus 3x to the power 2. Subtract, let's say 5. Is this even or odd? Even, right? Even function. But what about this -5? Why is that even? Anyone? Yes? Yeah, so it's like almost an imaginary. So this -5 is like -5x to the power 0. Because any number to the power 0 is 1. So x to the power, any number, again, remember, x to the power 0 is equal to 1. So these are all 8 is even, 4 is even, 2 is even, and this 0 is even. So it's an even function. So this is an even function. Because all the powers of x are even. Numbers. And another point is, so its graph actually, it's symmetric around the y-axis. And get that intuition from this example x squared. That's symmetric around the y-axis. Even functions are symmetric. So this is that cool thing about even functions, is that their graph is unchanged when flipped around that vertical axis or that y-axis. So this example is an even function. So we can show this algebraically. And this is like a mini proof. So you can kind of see the thought. So let's write down the function and show it. So that's the function. By definition, now we want to show with a negative x, what happens? So we plug that in. This is negative here. So negative x to the power 6. So this would be equivalent of -1 or negative x times negative x times negative x times negative x times negative x, 1, 2, 3, 4, 5, times negative x. It's the same as negative x to the power 6. You see, negative, negative, this makes a positive, negative, negative makes a positive, and negative, negative makes a positive. So this is going to be positive, so 6 to the power, x to the power 6. And we see negative and negative, that's going to be positive, plus 7. So therefore, we can see this. Therefore, this function is an even function. And its graph is symmetric. Around the y-axis. And back to that symmetry property in this x squared, remember our parabola here, this was symmetric around that y-axis, so this was even. Now, the next thing we're going to talk about is odd functions, as you probably recognize. So an odd function, by definition, is, so we have negative in front of the x, and then we take the function, or it's equal to negative f of x. So to check if it's odd, we're going to use this definition. So this function f, and remember we're again talking about something of this format where f of x is equal to like a polynomial of this idea. And it might stop here at an x to the power n. So this is called a polynomial. And it's odd function of all the powers of these x's. So these variables, the x's are the variables, and the a's are basically the coefficients. So the powers of these variables in f are odd integers. But there are many other odd functions. So this also means that f cannot have any constant term other than 0. So this again is our definition, and it holds for every x in the domain of f. So this expression must be defined to start with. So for example, again, a function whose domain is -2 to 1 cannot be an odd function because the domain extends all the way from -2 to 0, but only 1 on the right of 0. So you need it from, like, let's say from -2 to 2 because of some symmetry, not exactly symmetry, but symmetry along the origin. So this awesome thing, before the even function was symmetric around the y-axis, the odd function is symmetric-ish. So the graph is unchanged when flipped around the origin. And I'll explain what that kind of means a little bit more. So here, I'm going to write some examples. So let's say you have a function like this, 4x to the power 5 plus 2x to the power 3 plus x. Is this even or odd? It's odd, right? So this is an odd function. Because all the powers of x are odd integers. Oh, so you just check them. So 5 is odd, 3 is odd, and there's an imaginary 1 here, and that's odd. So we know they're all odd. What about example 1? Another example. So 6x to the power 3, let's say plus 5x plus 7. Is this even or odd? Okay, it's not. Anyone else? I just said no, so therefore, the other option is, okay, well, it's not an odd, no. So just say not an odd function. Why is this?
0.
Yeah, because this is a constant here, right? Like the 7 is a constant, so it's like an imaginary, let me write that. It's like there's 7 times x to the power 0, which someone said out there. Can't tell with a mask on. So put up your hands just so I can. So this is obviously an even, the 7 is even, and these are odd though. So because not all powers of x are odd integers. So I'm just going to make a little, well, I'll come back there. One more example. X to the power 3. So we were talking about x squared. This is obviously an odd function. But what does this function look like? So what does an odd one look like? So something like this. So this is unchanged when flipped in this origin here. So it kind of like goes up like x squared on this side, but it's not symmetric in the y-axis. So if you take a point here, the distance from here to here versus here to here, sort of like flipped in this imaginary axis this way, so along the origin. So this is the picture of it. So when I say flipped across the origin, it means symmetric around the origin. So another way of saying this, symmetric around the origin is what it means. So that's a bit of the picture. Now, again, we're going to show this, and you can graph this online using Desmos, which I just showed, but we're going to use the definition. So the definition of odd is that there's negative f of x. And we're going to check if this is equal to f negative x, or f of x to be an odd function. So we can write it down. F of x equals negative 5x to the power 5 plus 2x to the power 3 plus 4x. A negative out front, just put that in front. So it's in the same thing, negative 5x. Negative and negative make a positive. Distribute that negative in. And now we check this right hand, f negative x. So I'm just putting it in here, just plugging it in and then computing it. Now you see the negative x to the power of 5. Well, that's odd. So negative and negative will make a positive, a negative and a negative will make a positive. You're left with one more negative. So there's going to be a negative here and a negative here. So that will positive, right? So that would be a positive. Same thing here. 2 negative and negative will be a positive and one more negative. So the negative will be out front. And here there will be negative 4x. You see this and this, they're the same. So we can see that negative f of x is equal to f negative x. Therefore, it's an odd function. Okay. Now this function, 1 over x. So where is it not defined? Of course. What can you not do with this function? 0. So it's defined for all real numbers except for where 0 is, except for 0. It's an odd function. So we're going to show this algebraically, and we're also going to draw its graph. Ooh. So to show this, and this is also another function that comes up frequently, like if you take calculus in your future. So x squared, 1 over x, you're not going to get away from this function. So to show that this function is an odd function, we have to check the definition. Check the definition. If so, f of x equals 1 over x. F of negative x is going to be 1 over negative x, which is just equal to negative 1 over x. And negative f of x is equal to the same thing, negative 1 over x. So they're the same thing. So we can see by the definition, it's kind of recursive, but it's important to see, check the definitions, because that's the idea in mathematics. You have by definition this, and then you check the left and right hand side. Like that's the idea of how to do a proof in math. So and not that you have to worry about difficult proofs. But it's the training. So we can see that by definition, this holds, and therefore it's an odd function. So how to draw this? What does this function look like? So at 0, it's not defined. So you're not going to put anything when x equals 0. What about when x equals 1? Well, we got 1 over 1. So it's here. What about x equals 2? Get 1 over 2. 3, etc. here, so on. What about when x equals a half? You're going to get 2. Now, when x equals -1, we're going to get a -1 here. X equals -2, we're going to get a -1/2, etc. So you can start like plotting some points in your head or do a table of values, and then you connect the dots with a smooth curve. This is where I really struggle. So the graph kind of looks something like this. Imagine it's smooth and the lines are nice and straight. So, but it's the idea of first thinking about the points and then just plugging them into the function and plotting those functions. Again, here at 0, it's not defined. So you see it goes kind of from -infinity all the way to -infinity along the y-axis, and from positive infinity on the y-axis to positive infinity on the x-axis. Now, can you think of a function down here whose graph is even and odd at the same time? And you see that this is odd, it reflects around the origin. So what is both even and odd? Anyone? It's not a very interesting function. Yes? Right, yes. Yes, that's the function. Good. It's a little bit, yeah, not very interesting. So the function f of x equals 0 is both even and odd. Good. Yeah, but again, not interesting, x equals 0. But you see it would be even, it would reflect along the y-axis, and it also reflects around the origin, and it's the same graph. So yeah, so you can think of the picture kind of composite functions. So we learned how to apply some operations on functions to obtain new functions. We can do more. So in fact, I kind of like this topic because it lends itself to lots of applications like later on. So we can do more. In fact, we can also obtain new functions by combining two given functions. So algebra on functions. We take two functions, f and g. The sum, difference, product, and quotient are defined. Essentially to sum, to add two functions. we add them, right? So so we can add the functions f plus g, and then this is our input. So it's just going to be f of x plus g of x, or we can take the difference this way. The product, you can multiply the functions and then apply the input to the functions or separately. And the quotient, as long as when you divide by a function, the bottom function does not equal 0 there. So those are kind of intuitive. But let's see some kind of examples. We see that addition and multiplication are commutative. So you can add f plus g or g plus f, same thing. They're associative, but of course, subtraction and division is, you can't do that. You can't subtract g minus f, because this is kind of like the operators acting on the functions. So you cannot take g minus f is not equal to f minus g, or f divided by g is not equal to g divided by f. Let's see examples though, just to put it in perspective. So let's say you have f of x equals x squared minus 3, and g of x is equal to 7x plus 4. Okay, so we're just going to add them. So f plus g is just simply, by definition, you just add them. I like putting brackets around things just to make it clear, like this is your f of x, this is your g of x. Similarly, when applying or adding, remember we have a quiz on Thursday. When adding or subtracting fractions, it's nice to put brackets around things. And then we add. Next one, same idea. Subtracting here. And you get x squared minus 7x, and then minus 7, yeah. And then f times g. Okay. We apply, how do we multiply these? Reminder from high school? Anyone? Pardon?
Distribute property.
Yeah, distribute, that's right, yep. So we can distribute, the word from high school is FOIL, first, outside, inside, last. If you does everyone know FOIL? Put up your hand. Okay, good. Hallelujah. Great. But distribute is what I said previously, so that's perfect too. So we're going to distribute that x squared. And then the last one. It's just going to be x squared minus 3 divided by 7x plus 4. The bottom, of course, cannot equal to 0. So this comes to the question of domains. So how do we find the domains of these functions? So these functions exist only where it makes sense for the functions to exist. So the first one, the first three seem okay, but the last one can't divide by 0 and we're dividing by something. So it depends on where the domains make sense. So where F and G make sense. And we have to be, of course, careful not to divide by 0, even dividing a function. Like a function could be equal to 0. So the domain of the first three is the intersection of the domain of F and the domain of G. You have to be careful about this division of 0 of F divided by G. That's the intersection of F and the domain of G, except for the values of X where G of X equals 0. So it can't be where basically G of X equals 0. So the domain of F divided by G does not contain those values, let's say, that make G of X equals to 0. The other three, so the domains of F plus G, F minus G, and F multiplied by G consist of all X values that are in the domain of F. And in the domain of G. It's just at the bottom one, at the last one, the quotient of F and G, the denominator is G, and if that's equal to 0, it can't contain that. So I had to just say a few things about these domains. So like, it's easier when we apply it to an actual example to understand, to get a flavor of what we're doing. So suppose F and G are like these functions defined. Evaluate the sum of the functions and evaluate it at 6, and the product of these functions and evaluate it at 6. So let's write that down. So F plus G, we're going to evaluate it at 6. So it's going to be F, we're adding them, and G. Now, function of F is square root of 6 minus 6. So square root of 6 minus 6 plus G. So G is square root of X minus 4. Well, X in this case is 6. So 6 minus 4. We have the square root of 0 plus square root of 2. So our answer is square root of 2. The next one is the product. Evaluated at 6. So we have F times evaluated at 6 times G evaluated at 6. So again, 6 minus 6 times square root of 6 minus 4. Here we have square root of 0 times square root of 2, which is 0. Okay, so we evaluated them. All right, so that's that first part. The second question says find the domains of FG, F plus G, and FG, the product. A little bit more. So F of X is equal to the square root of 6 minus 4. So this part here has to be, when you take the square root of a negative number, can you do this? No. So if you have a calculator out, just try to take a square root of a negative number. You're going to get an error. And so that's not defined. So this, anything in the square root has to be greater than or equal to 0. So this domain, so this implies the domain of the 6 minus 4 is going to be greater, or sorry, I'm looking at the 4 in front of me or above it. 6 minus X is going to be greater than or equal to 0. What does that imply then? That implies 6 is greater than or equal to our X. Oh, wow. Well, we can draw this. We kind of know from, we did intervals, draw the number line. So let's say this is our 6. And our X is anything below it. Okay. What about our G of X? So G of X is the square root of X minus 4. So this will help us get our domain. So our X minus our 4, that has to also be greater than or equal to 0, because we cannot take the square root of a negative number. So this has to be greater than or equal to 0, which implies if we move the 4 over, X is greater than or equal to 4. So we can draw that. Let's see. This is our 4. So it's on this side. Okay. So we could label this. This one goes from negative infinity to 6. This one goes from 4 to positive infinity. Okay. So that was the domain of F, the domain of G. F plus G in the product. So let me write a little note. So that was the domains of those. Now changing colors, we see where do they both live? The X values that the sum and product make sense. Where would that be? Right, yeah, 4 to 6, right. So we can kind of like draw here and here. This is like from 4 to 6. So we can see, let me put it in words, that only X values in 4 to 6, including those endpoints, are allowed as input. for f plus g and f times g. So the domain, therefore, of f plus g and let's say, I'm just going to combine them, is 4 to 6. Okay, good. So composite, this is an important topic. So this is more interesting. Oh. I'm recording. So this is a more interesting way of combining essentially two functions. It's to take this thing called our composition. So we're composing two functions is this necessary tool when dealing with applications where basically one function depends on another function. We basically take a function and substitute it into another function. So the composition of f and g are functions, and it's denoted f, this like little circle thing called g. So it's read as f composition g. And it's defined this way, f of g of x, where we basically take the input x, plug it into g of x, and then take that input of g of x and plug it into our f of x. So this is that composition of f and g. So when evaluating f of g x, we first evaluate that g of x, like we've been doing with regular functions, just evaluate it. Then we evaluate our g of x and we put it into f of x. And we evaluate f at g of x. So the domain of f of g is the set of numbers x such that f g of x is meaningful, where basically it has some sort of meaning. Therefore, the domain of f of g is the set of numbers x in the domain of g such that g of x is in the domain. Let's kind of like draw a picture first. I might come back to this. So like, let's say this is the domain of our domain of our x. And then we apply that g of x. So it's the same thing. We're applying, we're taking this x, we're applying it, and we're getting this. Now we have this g of x. Let's say it's this area. And we're applying our f. Let's use a different color. And then you can go back here. So that would be our domain. So the question of the domain is which X values are allowed as input, essentially. So let me write this down. And I'll show you an example. So essentially it's only those X values and then domain of G for which G of X is in the domain of F of X or F. That form the domain of F of G. So we have the X values again, and then we have a section. We apply the function G, and then we have applied the function F. And depending on whatever those, I know it's a bit abstract at this picture point. It depends on what those functions are. So the domain again is this area here. Okay. So we'll see an example. So we have these two functions, f of g. We're going to evaluate the composite. So they're kind of interesting. So let's see. What do we do? So we have the function it's equal to, well, let me write it down. F composite G evaluated at -1. So this is where our X is equal to -1. It's equal to F G at -1. So we leave, it's again the idea of inside out of that bedmess where we evaluate what's inside the brackets first. So we leave the F alone for now, and then we plug in a -1 into G. So our G is X cubed plus 2. So this would be -1 to the power 3 plus 2 and bracket. Okay, what is that equal to? Anyone? Okay, you're right. -1 plus 2 is 1, right? Perfect. Now we take this 1 and we plug it into F. So that is equal to 2 divided by 1, because X's are 1, minus 3. And that's equal to 2 minus divided by -2, which is equal to -1. Okay, good. So that's our answer for part A. Part B. So now we're going to evaluate G of F at -1. So it's the opposite. So G of F at -1. Let's do that together. So we leave G alone. F at -1, rewriting it. So -1 plugged into F is 2 divided by -1 minus 3. Evaluate this is 2 over -4. This is G at -1/2. I think someone said that in the audience, right? -1/2. Now we plug this -1/2 into our G. Well, our G here is x cubed plus 2. So we write that in. And evaluate, and we get, anyone? Just raise your hand. Yeah, minus 0.125 plus 2 is 1.875. Got that? So, okay, let's find a formula. Wait, actually, before we do that, what did we just notice here? Something interesting. So notice something. Let's stop. So make a little note. So note that f of g at x is not the same as a g of f at x. So that's kind of interesting. So f of g, so it doesn't satisfy one of those properties. I'll let you think about which property that is. So find a formula for f of g. So we rewrite it as we do. Same thing. So g of x is going to be x cubed plus 2, and we're going to plug that into f. So f is 2 divided by our x. Well, x here is x cubed plus 2. So we plug that in. Minus 3. You can put brackets to indicate. And then we simplify. So this was the equivalent of saying 2 divided by g of x minus 3. And g of x is this. So let's find a formula for composite G composite F. So the reverse. So G F of X. So this is the same as having F of X to the power 3 plus 2. So F of X was equal to 2 divided by X minus 3 but this whole thing is cubed and then plus 2. Now, the next question, find the domain of f of g. So we have, remember, our f is equal to 2 divided by x minus 3, or g of x. Let's remind ourselves what these functions are. X cubed plus 2. So the composite is just f g of x and g of x is the whole, let me write that. So the domain of g of x is just the real number line. It's the real numbers. So all of them. This is a kind of like a roundabout way of doing it. So then the domain of f of g is all the x from the domain of g for which g of x doesn't equal to 3. So this would mean if this g of x were equal to 3, we would kind of have a problem. So we can write that out. G of x equals 3 means, well, what is g of x? That's equal to x cubed plus 2 equals 3, which implies if you solve this, x equals to 1. So therefore the domain of f of g is all real numbers except for x equals to 1. So therefore, the domain of f composite g is equal to the real numbers. Subtract that 1 point when x equals to 1. This would be f, sorry. And I'll leave this last one as an exercise for you to do. But you can see back to E, if you look at here, f composite g is 2 divided by x cubed minus 1. Well, this won't be, if this were equal to 1, the denominator would not make any sense. So this is logical. Now, so an actual like application of this composition of these functions. Now, suppose your cell phone company charges you 0.08 per minute plus 0.7 for each call to, like, let's say Hogwarts. So it charges you this fixed cost plus per minute charging. So a fixed cost plus and that's the cell phone company. So we're going to find a function, let's call it P, that gives the amount charged by your cell phone company for a call to Hogworks as a function of the number of minutes. So the number of minutes, let's just define what it is. Let's say M is equal to this number of minutes. And let's find this function, this P. So P, well, we're going to be charged per minute. So each minute, so let's say, 5 minutes. So 5 times 0.08 plus that fixed cost. So it's going to be 0.08 times the minutes plus that fixed cost. Don't keep paying it. So that's what the company basically charges you. Okay. Sorry, this is B. Now, I guess it automatically changed. So suppose the tax, now the company charges you a certain amount. Now the government also now charges you a certain amount of money. Suppose the tax on a cell phone bill is 6% plus 0.03, another sort of like fixed cost by the government. But this 6%, let's say, is addition to the actual cost. Like the company charges you a certain money, and then the government also, again, charges you like taxes, like 13% HSD or something like that. So this is 6% in addition to the actual cost. And this is the fixed cost. So find this, so it's first just good to slow down and read like these word problems. So find a function T that gives your total cost, including the tax for a call to Hogworks as a function of the amount charged by your cell phone company. Okay. So the tax, let's call it this T tax or something. It's going to be a function, let's say of X, and it's at 6%. So we pay the amount plus 6%. So it's going to be that 1 times 0.6 times our X plus 0.03. So this is what you pay. Now we're going to find a formula for this total cost to get that total cost, a formula. So this T, let's call it total cost. Is equal to, we're going to take 1.06 and we're going to multiply it, put in our total amount that the company charged you, which was 0.08 times the number of minutes, plus 0.7, plus 0.3. So essentially what we're doing is we're putting in what the company charged, which was P, as a function of m, or let me rewrite it a few different ways. Composite with the tax of our minutes, which is the equivalent of saying t writing it this way. Which is, again, just rewriting it. So this is really just the composite, because we have like the tax of what the government charges. So first we have what the company charges, and then the government obviously charges you tax on that. So what would your total cost for an 8-minute call to Hogwarts be? So let's say your minutes are 8 minutes. What is this total cost? Well, just plug it in essentially into this function where m equals 8. And then you just compute it and do the arithmetic. So then the total cost is going to be $1.45. So it's possible, of course, to compose more than 2 functions. The idea is to take 2 of the functions and then you compose them, and then compose the result with the next function, and so on. So it basically has like this nice property of functions is that it's associative. So for example, F composite G composite H, you can first composite the first 2 functions, then composite that with H, or you can compose the last 2 functions and then compose that with your F. So the associative composition of functions allows us the freedom in which what order we want to do the compositions. And so it depends on what those functions actually are. Some might be easier or more difficult. So it's about thinking which one should we compose first. So for like this example, where we have F, G, and H, let's write it down and try to work on this together. So x plus 8, G of x is going to be x squared minus 4. And our h is going to be x minus 2. Okay. And we want to find the composition. Okay. So there's different ways of looking at this. I don't like to work with these square roots. Like, this is a little bit annoying in my opinion. So we might want to like leave that to last. So let's write this down. Like, you could do it F composite G, but then you have to work with the square root. Like, so let's try to avoid it. So, and make a little note why. So using, let's say, F composite G of H, it would be better perhaps instead of F composite G first, then H. It seems to be a little bit simpler, I would think. Because we don't really want to deal with the square root, this stuff, too many times. So, okay, so we're going to deal with the G of H first. So this again is the equivalent. F of G. We plug this in. So the G in the H into the G. So we have the H and we plug that in. So x minus 2 squared into our G minus 4. Now we simplify this. What do we get? So expand and simplify. So x squared negative 2x times negative 2x, negative 4x plus 4. And then we have to subtract 4. So this is F composed of this stuff. So the x, the 4's and the 4's cancel, get x squared minus 4x. Okay. Now we can plug x squared minus 4x into our f of x. So we just plug that in. We have square root, we have x here. So it's x squared minus 4x. And then we have plus 8. And that is our answer. So then we only had to deal with that square root one time. So decomposition is sometimes when given a composite function, it's important to find the ingredient functions that make up the composite functions. And you might want to remember this later on when you're trying to integrate or you take a calculus course. So this is called decomposing a function, essentially. It's usually done by inspection rather than any precise procedure. So it's just by kind of like looking at the functions and determining how to decompose them. So here's an example. So suppose we have like this function, m of x equals the square root of sine 2x. Let's rewrite it as a composite of three simpler functions. So we're going to basically, so we want basically f, a g, and an h, such that m of x is going to be a composition of like these functions. So we could take So what do we think these functions are? Anyone? Yes? Square root of 2? Of which one? There's three functions. So we want to find f, let's say h of x, g of x, and f of x. That we get these functions when we take the composition. So what do we think, let's say, f of x is? Yes? Three functions. Let's try again. Yes?
Square root of x.
Yeah. So f of x is the square root of x. Because that's the other outside one. Like our previous example, we left the square root to last. So that's our last one. Now we plug something in for x. So someone said sine. So that would be a good idea. So sine would be this one. And then what are we plugging in for our x here? See right here. 2x, right, 2x. Perfect. So it's kind of like by inspection. It's like a game almost. So that our m of x is going to then therefore equal to f of g of h of x. And we see our composition here. So we see like that we plug these in. So we take 2x first, we plug that in. Then we take our g of x, which is equal to our sine of x, plug that in, our 2 of x into our sine, and then take the sine of 2x and plug it in to our f of x, which is the square root of x.